Let's take a look at how to solve problem 319 from the homework. And we're going to solve this a little bit differently. We're being asked to find I0 in this circuit. But instead, what we'll do is we'll actually solve the entire circuit, meaning that we'll determine all of the node voltages and all of the branch currents. We're going to do this using nodal analysis. And when we do nodal analysis, we have a very formal method that we use. First, we select a reference node, then we label node voltages and branch currents, remembering to assign directions to those currents. Then we apply KCL and solve for the node voltages, and then finally back solve for the branch currents. Okay, so let's start doing that. So we'll assign our reference node down here at the bottom, and then we'll label and assign variables to the node voltages. Okay, so let's call this one V1, or I'm sorry, let's call it V0, and then we'll call this one V1, and we'll call this one V2. Okay, and then let's label and assign directions to our currents. Okay, so our currents, we can arbitrarily assign directions to them. The only one that we're forced to, well, not really forced, but the only one that it makes sense to look at here is this one here, where we're already given the current direction. So in order to obey the passive sign convention, we'll assign our current like that. Okay, and then finally, let's also give these values. We have I0 already, so I1, I2, I3, and IV. And we already know this one right here, so we don't need to label it. Okay, so now we're ready to apply KCL. At V0, we don't really need to apply KCL in order to determine the node voltage because it's 12 volts. Okay, V0 equals 12 volts, and that's positive 12 volts because of the polarity on this voltage source here. V1 is a node where we will have to apply KCL. So I like to write down what I'm doing here, KCL at V1. That way, if there's a mistake in my work, I can go back and make sense of what I've done. And also, when you're just getting started with these, it's helpful maybe to draw little arrows that let you know what's coming in and what's going out of the node. Okay, and now we'll start over here, and we'll assume that going into the node is positive. So V0 is at a higher potential because of the current direction that we've chosen. So it's going to be V0 minus V1 over 3K. And then plus 2M, right, because that's also going in. And then going out of the node, we assign a negative, and that's going to be V1 minus 0 because of our current. Again, it just happens that V1 is a higher potential than our ground, so it's going to be V1 over 6K equals 0. Okay, now let's put this into standard form. So I have a common denominator of 6K, so I'm going to put everything under a common denominator, or put these two terms here under common denominators, and then multiply through by 6K. Okay, so I get 2V0 minus minus 2V1, 3K, I'm sorry, 6K times 2M equals 12 minus V1 equals 0. Now let's combine our terms and simplify. 2V0 minus 3V1 is equal to negative 12. Okay, and that is our first standard form KCL equation. Now let's solve for V2. KCL at V2. Again, I'll draw some arrows to keep me from making a mistake. And we'll just say that going into the node is positive. So we only have one current coming into the node, and given the way this is set up, V0 is going to be the higher potential, so it's going to be V0 minus V2 divided by 4K. V0 minus V2 divided by 4K. And then the other ones are leaving the node, so we put a negative value in front of them. Negative 2m and negative V2 over 2K. This is all equal to 0. And now we can use 4K as our common denominator, and we'll end up with V0 minus V2 minus 8 minus 2V2 equals 0. And finally, V0 minus 3V2 equals 8. Okay, and now we are able to take these equations and solve them. And there are a couple ways that we could solve them. First of all, these equations can be solved independently of one another because in this equation we know V0 and we only don't know V1, so we can solve for that. Okay, so 2V0, which is 2 times 12, is 24. Subtract from both sides, we get negative 36 over 3, or V1 equals 12. Okay, and in this situation, we get V0 equals 12. So 8 minus 12 is going to give us minus 4, and so we'll get 4/3 for V2. Okay, and so we've solved all of the branch voltages, and it's really a matter of simple math now to go back and solve for the branch currents. Okay, because recognize that this right here is I2. This right here is I0. This right here is I1. And this is I3. Okay, so the only current that we don't know is IV right here. But we can use KCL. We can use the KCL equation that we didn't write, the one at V0, if we write it only in terms of the currents, then we can solve this equation. So we would have I1 going this way, I2 going that way, and we can say that IV is going this way. Okay, so that's going to be, let me write it up here. Okay, we'll use our color here for the node. So the KCL equation here is I1, IV minus I1 minus I2 is equal to 0. Hence, the current in the voltage in the branch with the battery is equal to I1 plus I2. Okay, and so that way we're able to solve for all of our branch currents. And I have gone through and solved those in Mathematica. Okay, and if you're familiar with Mathematica, then you can just look at what I've done here and hit enter or shift enter, and you'll get your answers. If you're not familiar with Mathematica, let me just point out a couple of things. What we've done here is we've created a variable called sol, and we've set it equal to this thing here. This is going to spit out a table of assignments for V1, V2, and V3. And you'll notice that these equations have a double equal sign. Double equals actually means equals, and a single equals means set. So it really means set the left-hand side of the equation equal to whatever it is that's on the right. So SOL is actually going to end up being a table of values. Okay, and this is a more arithmetic vernacular for an equation, is to use the double equals in Mathematica. Okay, and then in the second equation, or the second line of code here, what has been done is all of the branch currents have been written in. And then this is saying to assign the values that are obtained in sol, or that are contained in sol, and apply them to the variables inside of these brackets. Okay, so when you run the code, it tells you what V1, V2, and V3 are. And then finally it plugs V1, V2, and V3 into here and spits out the values of the currents. Okay, so I hope that's helpful.